Okay, welcome back and let us continue the discussion on combustion chemistry. So, we are looking at the different aspect of kinetic mechanism, elementary reactions and the impact of the free radicals when they are present in the system. So, and then we have looked at a particular example of hydrogen oxygen reaction. So, now we will look at some more example like carbon monoxide oxidation and CO oxidation. So, this is another important reaction, that CO oxidation, because any hydrocarbon fuel that we burn, for example, CXHY, any hydrocarbon of this series whatever we burn. So, intermediate radical, one of the important radical is the CO radical, and a CO, if it is completely burnt or oxidized, it will give you a CO2. It does not, then it will remain as a CO, and which is one of the major concern of your emission. Now, also a very simplistic point of view, can you have two steps this can happen for a hydrocarbon fuel. One is the breakdown of fuel to CO, that means where CXHY forms CO, then as I said CO forms CO2. If the combustion is complete and there is nothing excess and everything goes smoothly as per expectation, then you will get as a end product CO2. Though CO2 also has problem in environmental issues, but CO is much more problematic. So, another issue what is kind of challenging is CO oxidation is extremely slow in the absence of small amounts of H2O and H2. So, now if H2 is the primary hydrogen containing species, one can describe the CO oxidation by this set of mechanisms. The first reaction for CO oxidation, CO will combine with oxygen and form CO2 and O radical, then O will react to H2O, form OH and OH radical. These are again some of the highly reactive radical as we have seen earlier. Then again the CO will react with OH to form CO2 H radical, H will react to O2 to form OH, and so this is a series of oxidation step one can. Now, if you look at each of these individual reactions, CO1 is slow and also contributes quite a bit of CO2 formation. So, this is sort of an, one can say it is a chain initiation reaction, and the third reaction is actually the CO2 CO oxidation step. So, this is in sort of a chain propagating step producing H atoms. Now, you got this one and this one, then remaining reaction 2 and reaction 4. So, they are sort of chain branching reaction which produces OH and H, and CO2 reaction is the key for your CO oxidation. Now, if hydrogen is present, then some of these steps are also involved. There will be few more steps, oxidation step of CO 5, 6, 7, where O react to H2 to get OH plus H, and then OH to H2 to get H2O and H. So, these are, mind it, these are free radicals. So, these radicals are highly reactive and they do take part in this reaction process aggressively. Then finally, CO react with HO2 to get CO2 and OH. Now, when you have H2, the entire H2O2 reaction system should be included in the CO oxidation. Now, one can look at the general system of these things, higher paraffins, where alkenes and paraffins, these are saturated straight chain or branch chain single bonded hydrocarbon. So, one can actually represent them in a series CnH2n plus 2. For example, if CH4 where N is 1, So, you get 4 C2H6, then C3H8 and so on, which will methane, ethane, propane, butane, like that. Now, generic oxidation discussion will be for n greater than 2, that means we will start from the propane and butane. Methane or ethane display some unique characteristics not common with higher alkenes. So, these two at the where N0 N1 and N2, they show some different characteristics compared to higher order hydrocarbons. So, the whole idea is that how we look at the alkene oxidation here. Now, there are 3 sequential process here. First, fuel is attacked by O and H, and then when that happens, it breaks down to H2 and olefin. So, which is a double bonded state hydrocarbon, and then H2 oxidized to H2O. So, that is step number 1, where you first react the fuel with O or and H. The next step, all these unsaturated olefins form CO and H2. Almost all H2 converts to water by that time. So, that happens at the second step, and the third step, CO bonds to CO2, releasing almost all the heat associated with the combustion. So, this is the step which is quite important and happens at the third step, where CO actually. So, now we can look at these 3 things with an example. For example, as we said, n has to be greater than 2. So, the simple one can take is the propane, which is C3H8. Now, with the propane, first step, the CC bond is broken into original fuel molecule. So, this is C3H8 and this should be broken into C2H5, CH3 and M. So, that is your step number 1, where fuel is sort of attacked. And why that is possible? That because this CC bond is weaker than an HC bond. Second step, 2 resulting hydrocarbon radicals break down further to olefin, H atom abstraction. So, this is called atom abstraction. So, here one is the C2H5, C2H5 react to M, form C2H4HM, and CH3, which will also react to M. So, these are the 2 important steps which happens or takes place at step number 2, which is obtained from the breaking of the fuel bond. Then step 3, whatever you get the H atoms or H radicals at step 2, they will start a radical pool. So, H will now start with O2, form O and OH. That means, now you start getting more and more reactive radical in the system. Initially, when these bonds are broken, you get H. Now, H will start reacting to O2, which is as a part of your oxidizer. It starts forming more and more reactive radicals like O, OH and so on. Now, when you start having more and more radical pool, so the fuel molecule intensifies. So, C3H8 again react with OH, starts forming these, it reacts with H, form these. So, these are the multiple steps that go on having a reaction with the fuel. Then step 5, what you get is, now the hydrocarbon radicals decay to olefin and H atoms via H atom abstraction. So, this is C3H7, which will get you C3H6, H and M. So, this process obeys the one of the common rule is the beta scission rule, which states that CC or CH bond broken will be the one that is one place removed from the radical site, which is C3H7 when it reacts to M. So, C3H6, H and M, or it can form C2H4, CH3 and M. So, these CC and CH bonds are broken and one get to form this, basically these broken bonds to form the olefin. So, if you look at this image which we just discussed in this particular step, which is a as per the step 5, as per the rule of beta scission rule, you can see what happened. This is the isopropylene radical, this is N propylene radical, this is the C3H bond. So, this is the radical site and this is the radical site, and then you, due to the decay, you get the olefin. Now, thereafter you go to step 6, where the olefins are now getting oxidized and then produces some other radicals like HCO or formaldehyde like H2CO. So, these are the radicals now formed when these olefins are reacted to the O radicals. Now, C3H6 which will react to O will form C2H5 HCO or C3H6O C2H4 H2CO. So, these are the component now which are produced due to the oxidation of the olefin. Now, this radical CH3, that is a methyl radical, or formaldehyde H2CO or methylene CH2, they oxidize at step 7. So, these radicals actually do not stay longer and they get oxidized later on, and then finally carbon monoxide oxidize following the CO mechanism as we discussed earlier. So, that is what you get the CO2, and if you put them in a figure, you can see what is the hierarchy of this reaction mechanism describing the alkane combustion. So, this is your fuel, higher order hydrocarbon CnH2n plus 2, that is first oxidized, then you get CH4 and C2H6, that means it breaks down to the lower order hydrocarbon and you get more like olefins, and then olefins actually produces these other radicals and those radicals oxidize, and then finally you get CO oxidation, and at the core you get H2 oxidation. So, essentially if you go in a loop, this is how it actually goes on in a stepwise fashion that we have already discussed. So, first one happens first. So, this is where step 1 to step 8, this goes in this way. So, what happens first and then what, like this. Now, when you come down to the global mechanism, all these features that you get to see when you are looking at the detailed mechanism, that means which has all intermediate species and radicals which are formed through the elementary reaction, but global models do not capture all the features of hydrocarbon combustion. They are quite useful for simple engineering problem, and as long as you can use them with their limitation. For example, if you look at CHHY as a single step expression where this much is burning, this is your reaction rate, it will form CO2H2, and the rate you can define as this expression through the Arrhenius expression. Now, if you for the same methane or rather CnH2n plus 2, you can go slightly detailed, that means some more step instead of single step, there are multiple step like 4 step mechanism. So, in 4 step mechanism, first you get lower order hydrocarbon, then that gets oxidized to form CO, then CO2 CO2 and H2 to H2. So, finally, you get the product species like H2 and CO2. So, but the higher order hydrocarbon first breaks down to a lower order one, and then from there it goes to. So, even if you take an example of a methane oxidation, how it goes in a different ways. This is first our methane. So, when it gets reacted to OH from CH3 radical, then CH3 get to C2H6, C2H5, C2H4, C2H3, then finally with the oxygen this radical. Or another path, you can get CH3 and CH3O, or this side you can get CH3OH, which you can form that, and you finally get to CH2O, where again it will form HCO and then HCO to CO and finally CO2. So, there is a big chain, this is called the chain of the reaction kinetics, and this is a core research topic people who are working in the kinetics area, where they form. Actually, as an engineer, you would be interested to look at the kinetics only. So, because you need the mechanism, so that you can actually handle or analyze your combustion process, but this itself, the kinetics itself, is an area of research where people look at and they develop different kinetics and try to give you I mean, that is why for even a simple methane mechanism, if one look at it, there are single step mechanism, 2 step mechanism, 4 step mechanism, 9 step, and there are multiple step mechanisms, and every kinetics has its own limitation, but there has its own advantage and disadvantage. So, more and more detailed mechanism you include, you can actually predict the minor species, intermediate radicals. So, these are the issues. Now, moving ahead, one more thing that we would like to look at is the nitrogen oxide kinetics. This is another important issue. The reason why, because most of the combustion process, as we have seen, they are the source of your pollution. Pollution means CO, NO, these sort of gases, but NO does not form so easily. It is not that like in any normal combustion process you get to see NO, but to get an NO you need to have certain level of the process, the issues. But if you look at the NO formation, but this is no matter whatever it is, it has the presence of this NO has a I mean serious health hazard or environmental concern. Now, what happens when NO2 oxidizes with the O2? It forms NO and also the ozone gases. This is not something one would expect in a current scenario across the world, that where NO is formed. Now, presence of certain hydrocarbons like unburned hydrocarbons from combustion, methane. So, slowly unbalance the previous reaction. What NO does? It has a serious impact, like it contributes to the destruction of the ozone in stratosphere. Secondly, it contributes to the production of ground level ozone. Also, it is involved in smog and haze and all these things. So, this has a serious concern. Now, as we see this NO forms, it is a part of your pollutant gas, that NOx forms from the combustion, but there are a different mechanism of the NOx formation. It is not like that is what, as I mentioned earlier, that you cannot have NOx form when you are burning candle, it may not be forming any NOx, but it will obviously form some CO2 CO. So, NOx formation has certain regime, like there could be 3 different kind of NOx or 4 different kind of NOx. One is the thermal NOx, which is oxidation of the nitrogen in the post flame zone. That means, when you have this flame or reaction zone, it is in the post flame zone where thermal NOx is formed. That means, it is highly dependent on the temperature. Then there is a prompt NOx. This is a formation of NO in the flame zone. So, that forms within the flame. Then you can have also N2O, which is formed due to intermediate mechanism, and finally, if your fuel contains some NO, that will also can lead to some of this conversion. So, as I mentioned, this is an important thing. The importance of these 3 is dependent on the operating conditions of and the fuel. So, depending on your operating condition, which kind of NO formation would be there or there would be no NO formation, it is highly dependent on the condition and the fuel. But as I mentioned, most of the devices you get to see the thermal NO, that is the main source. Now, why this NO production is given by, there is a mechanism by Zeldovich mechanism, where there are different steps through which the NO formation takes place. So, these are the 6 reaction steps, these are forward and backward reaction. So, how O radical react to N2 and form NO, N form react to N2 form NO, N react to OH form NO. So, they and also the reverse reaction is possible, like NO with N can form these things, but this is kind of thermal NO formation mechanism. Now, if you look at it, the contribution of the reaction 3 is small for lean mixture. and for rich mixture it is considered. So, that means if the mixture is lean, then this contribution is small, if mixture is rich, then this is considerable. So, this produces enough NO. Now, when you look at the forward reaction of 1, it controls the system and it is slow at low temperature, high activation energy. So, this is also very effective in post flame regime, where temperature is high, T is high, and also you get enough time. That means this forward reaction. So, essentially the forward one, forward reaction. Now, the concentration of 1000 to 4000 ppr are typically observed in uncontrolled combustion system, and reaction 1 to 3 you can calculate the NO. Now, one can estimate the concentration or the NO production rate from these 6 reactions. So, these are contribution of forward reaction, reverse reaction for the first, second forward, second reaction. So, we need also the concentration of O which is present there, we need OH, N and H. So, now when you go to detail kinetic mechanisms and the fuel used, you can calculate from those things, but otherwise one may actually very crudely approximate them and to be assumed that in chemical equilibrium, and then you can calculate these things if you assume that is in chemical equilibrium. Now, a moderately high temperature does not stay at thermodynamic equilibrium. So, this is one important observation. If you have moderately high temperature, then N atom or that does not stay at thermodynamic equilibrium. That means, even to evaluate that, if you use this chemical equilibrium assumption, so that may not be appropriate depending on your again operating condition. So, in that case a better approximation could be assumed N to be at steady state. Now, if that is the situation, then you can write that dN by dt the production rate. So, this is coming from your forward reaction, and this is what we have get from these 3 reactions, where now you are writing for N, then this is forward, reverse, second reverse, forward, second reverse, third forward, third reverse, and to be in steady state this is equal to 0. And then if you do the algebra from here, which will be bit involved, you can find out the N at steady state, and which will involve all the different species concentration and reaction rate coefficients and everything. So, then you can find out at the steady state what would be there. Now, the reaction rate constants, which are because this is an well established mechanism. So, these are available readily in literature, and one can actually look at that. The forward reaction rate coefficients, these are all in SI unit. So, this is your A, and all these cases this is your activation energy divided by R, this factor, and this is your T. First reaction reverse is like that, second reaction you have some T to the power 1. So, that means in this particular case you get some exponents 1. So, that N is 1 here. So, the second forward and reverse reactions contain some temperature dependence parameter, and these are the as usual A by R, T, and these are the. So, this you can find out any standard literature if you look at it. Now, we look at that talk about thermal NO formation. Now, if you look at intermediate mechanism, this is also important in very lean combustion. So, when you talk about very lean combustion, that means equivalence ratio less than 1. And now how you define this NTO intermediate mechanism? You have N2 reacting with O and other third molecule, it will form N2O, then N2 will react to H to form NO, finally NO. So, this mechanism is also important in NO control strategies in lean premix gas turbine combustion, because one would like to avoid this NTO intermediate mechanism, so that you do not. Now, it is well known or shown that the some NO is rapidly produced in flame zone. Obviously, because if it is a thermal NO, then it would be formed in the post flame zone, but before they would come to NO by thermal mechanism. So, this is known as Fenimore mechanism. So, general scheme for that, in that case hydrocarbon radicals is CH reacting with N2O and form HCN, and C form CN and all these things. Now, that is what you get, and then the conversion of hydrogen cyanide HCN to form NO is as follows. So, that means if you form this, and then you can, from now hydrogen cyanide will react to oxygen to form NCO. Now, NCO will form to NH and CO, and then finally you get NO. And this happens where you are in the zone where intermediate radicals are formed. Now, if your equivalence ratio is higher than 1.2, then the chemistry becomes more complex and it couples with the thermal mechanism. So, that means what happens? So, there are different situations where one is the, if we just to complete this NO business, this is where one could be thermal NOx, which is actually in the active in the post flame zone, and that because the temperature is quite high. Then in the flame zone you can have prompt NO, and that also depends what kind of operating condition is this. I mean, no matter what it is, all these things depend on the operating condition, and then depending on the fuel or in NTO intermediate mechanism, there could be some NO formation. So, that is why in regular daily combustion system you may not see NO, but in the large scale applications you do see NO. So, this is what we talk about different kinetics and then the mechanisms and how they impact the reacting system. So, that is all about the combustion chemistry that we want to discuss. So, we will stop here today and continue the discussion in the next lecture.